Hey there, awesome physics students. Let's talk about Newton's second law. Newton's second law is a big deal in physics. It's one of the most important ideas in this course. There's a lot in there, so let's break it down into a smaller framework. The central idea in Newton's second law is that forces cause acceleration. So let me write this down in a particular organized way. We'll have cause here, and that's force. And we'll talk about the effect here, and that's acceleration. Well, this is all well and good, but there's one important ingredient that's missing. And you can't forget this. There's a property sandwiched in between here. That property is inertia. Or it's measured by, inertia is measured by mass. So the more mass, the more inertia. And remember that inertia is the resistance to changes in motion. So it's the property that if it's moving in a straight line at constant speed, it wants to continue doing that forever and ever and ever. And the only thing that can change that is a force. So the way we can write Newton's law from this framework is that we have a net force, and that is going to equal the mass times the acceleration here. There's a lot that's going on in here, so let's break it down. First of all, these things are vectors, so I have to write these as vectors. So I'm taking the net force, and that's equal to a scalar, which is the mass that measures inertia, multiplied by the acceleration, that's the effect. This says many things. First of all, let's break down, what does this mean, net force? Well, net force means I have to add up all of the forces and get the total force. That is what net force means, is total force. So I use this sigma symbol here, and this sigma symbol means sum, or add them up. And these are vectors, so we have to add them like vectors. So we have to use all of our tools of adding vectors to add up all of the forces that are acting on an object, and that is equal to that object's mass times its own acceleration. So this is the net force. It's the sum of the forces. This is suggesting a process. So we're going to have to talk about how to do that process. And we have a lot of guidelines to help remind us how to do that, because it's very confusing. Another important point here is that we have the net force is equal to some scalar times acceleration. Those are vectors. This tells us that the net force as a vector is always going to be parallel to the acceleration as a vector. That is, if you know that the acceleration is up, the net force has to point up. If you know the acceleration is this way, the net force has to point this way. Conversely, if you know the net force points this way, that tells you that the acceleration must also point that way. These two vectors will always, 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 without exception, point in the same direction. Okay? So if you know the direction of one, you know the direction of the other, and there's a scaling factor in between, the mass. All right. There's a few other things that we want to talk about here. Force causes acceleration. So imagine you put a force on a man. Let's say the man's mass is about 100 kilograms, which is 10 to the 2 kilograms. That's about 220 pounds. That's not unusual for a man to have mass of 220 pounds. If you put a force on that man of a certain size, you're going to get, that's going to cause some acceleration. Now, what happens if you put that same magnitude force on something large like the Earth? And I'm choosing an extreme example so you can really see the differences here. If you put that same force on the Earth has a mass of about 10 to the 24 kilograms. So this is a little bit bigger than the mass of the man. Specifically, it's 10 to the 22 times bigger. So let me just be clear about what that is. That's 10,000 million times bigger. 10,000 million times bigger than the mass of the man. So that means that if we take the mass of the man, we're going to get a pretty big acceleration out of that. If we take that same size force and use it on the Earth's mass, the Earth has a gigantic mass, and this isn't to scale here, And so the acceleration is just going to be so tiny. I'm not even going to be able to write, let's see, the acceleration like that. It's just such a tiny, tiny acceleration. The acceleration, in fact, is going to be 10,000 million times smaller than the man's acceleration. So if you think about putting a force on a man, let's say the man sits in a car accelerates away, the seat back puts a force on the man to cause that acceleration. You put that same force on the earth and you're going to see nothing. It's going to be undetectable. Okay? So that property, so the point here is that yes, you're thinking about the force and that's going to cause acceleration, but do not forget about the property in the middle that is very important for predicting the effect size that you see. The last thing I want to point out is that the first law is contained inside of the second law. So the first law says that things move at constant speed in a straight line forever, never, never, until a force acts. Well, let's think about that. If the net force is 0, this implies then, based on this expression, that the acceleration is going to be 0. And of course, these are vectors, so the acceleration vector will be 0. This as 0 acceleration means that the velocity will be constant, and the velocity is a vector. So not only will the speed be constant, but the direction will be constant too. So that means that things, if there's no force, things will move in a straight line at constant speed forever and ever and ever. And this is just from the second law. The thing is, this was such a big deal and such an important idea that things don't have a natural state at rest, that it was very useful for Newton to put this in separately and state it explicitly in a first law. Okay, so this is a short introduction to the second law. We'll explore the consequences of this in many other videos.